Good afternoon, everybody. I'm Sunil. I'm a solutions architect in the deep learning team here at AWS, and I'm here to talk about autonomous driving algorithm development on AWS. Yeah, great to see a great, all of you here. It's, who doesn't love autonomous cars, right? So let's talk a little more about how we can go out building and what are the components here that make this. So we'll start with the agenda. Driving, let's actually define what the driving development looks like in the runtime environment for autonomous vehicles. We'll then go with individual components, the problems. Let's look at how AI and deep learning actually fit in here. Let's look at AWS AI capabilities. Let's go through some of the data sets that we can get started. And then we'll do a live demo. Let's actually try and train a network, a couple of networks if we have time. And then let's look at the AWS connected vehicle architecture. And then finally, customer examples of how people have built this on AWS. Cool. So autonomous driving development, what's involved? Let's actually break this down. So we have the computer vision and the detection aspect. So whether it's lane detection, traffic signs, people detection, all of that come under this. The second aspect is localization. So you want to know what's around you and use that to guide where the vehicle should go. Path planning, right? So localization helps you, and object detection helps you where you can direct the vehicle. Another big component of this is HD maps. So not quite the maps that we all might use when we drive. That's not precise enough. We need centimeter precision, so HD maps for these autonomous vehicles to be driving. And the second aspect is the driving runtime, right? So what is it? How does the car actually run? So cars have many sensors, correct? So how do these interact with each other? So sensor fusion, how do we get all this compute locally there in the car? The second is HD maps that we talked about. We have edge computing. So what it was alluding is we have a lot of sensors, we have a lot of data, maybe you're connected to the cloud, but ultimately the decision needs to be happening at the edge. And not just the sensor part, the AI, if you're doing detection of objects and lane detection, all of that still happens to be done at the edge. So for development environment, what is it that is required, right? We need terabyte data acquisition. So a car can probably produce 20 terabytes of data if it has a lot of sensors, and this is more of a practical number that we see. So HD map creation, so whether it's usage of just visual cameras, but more often than not, you're using LiDAR to actually create HD maps. And of course, tagging of those images, and a whole process of like, how do you, okay, now I have the data, I actually need to annotate the data. So if people are familiar with supervised learning, what we need is not just the images, we need to know what is in the image and so on. And then the algorithm training itself, and of course, testing. In the runtime requirement, we need the mechanism, right? Like these HD maps are not small amount of bytes, so how do we efficiently update the maps? Or let's say you're driving from San Francisco to LA, well, you're at Big Sur now, you don't need to have the entire map, right? Like how do I get the map onto the device or the car, and so on. Localization, caching, so you want to have a state. You can't be reactive in a driving environment, right? You need to maintain some of the states. So how do you kind of incorporate that in at the edge? So what does AWS bring here to the table for these problems that we've set up, right? Petabyte scale. So petabyte scale, so we have Snowball, Glacier, S3. So cheap storage, cheap scalable storage that is available and different tiers of storage, right? The next aspect is, okay, now I have the data in AWS. What do? I need to do machine learning, right? Like I need to figure out what's in the data, figure that out. So we've got Amazon ML, we've got recognition, we've got a whole suite of platform that I'll walk through that can help here. And not just that, right? Like we actually need the underlying hardware because we're talking about terabyte, petabyte scale data. So you need really fast hardware to do that. So we have the latest P3 instances with the Volta chips, which are phenomenally fast. So in my experience training algorithms, they've been like, especially with vision and video algorithms, they've been about 5x than the P2 instances with the Tesla K80. And yeah, not to leave out the FPGA instances as well, where if you wanted to customize something really specific and really get the bang for the buck, you can go to that level of detail where you're actually using the VSDL to get the FPGA tree. And on the runtime environment, so you're getting a lot of data, so you can use the CloudFront acceleration to ingest data into S3 with the S3 acceleration. You can use the serverless model where needn't be driving the car per se, but a lot of data collection or building that integration from an analytics point of view could be helpful with Lambda and API Gateway. There's one key component here, not necessarily is get left out when all of the excitement is security, right? We need a secure way to get all this data into the cloud. And that's where AWS IoT comes into the picture. So X509 certificates, you can burn them onto the device at the edge and securely communicate, establish a pub/sub mechanism and actually get the data securely onto AWS. But additionally, what we have is also Greengrass, which provides compute at the edge. So serverless compute at the edge. So think of it as Lambda at the edge, where you have your serverless capabilities. The same programming model gets you get to use them at the edge. So pretty fantastic to actually be using that service because you're not changing your programming model. And not to forget IAM there to actually manage the policies on your data ingest, accessing, all of that. So where does AI and deep learning fit in here in this equation? Before that, let's just set the level straight on what does AI, ML, DL, all this stand for. So what I like to describe with AI is it's an overarching umbrella. So you can think of it as how can I do human tasks with a computer, right? How do I get that automated? So that's the overarching umbrella. And two approaches are machine learning and deep learning. And machine learning, the way to think about it is you're actually finding a function that fits the data that you have, so it understands that, so you can do predictions. Now, in the deep learning approach, what you do is you actually define a structure. You define a network structure that learns how this algorithm or how this data actually looks like and what is the algorithm that I need to think about and build that so that we can actually interpret the results. Now, if you look at the Amazon ML stack, we sort of went to the infrastructure level a little bit earlier. In case of deep learning, the middle two are the most useful. So the platform level, what we have is a lot of where you can get the data ingested, cleaned up, and ready to process. And now that is actually part. With EMR and Spark ML, you can do your machine learning and your data processing in the same stack. And framework is now we want to make it easier for people to set up deep learning environments, a lot of new framework updates, libraries. So we actually have the deep learning AMI, which is available at no additional cost, comes with including the NVIDIA CUDA drivers and frameworks like Apache MXNet. You have TensorFlow, Caffe, NumPy, SciPy, all those libraries actually get packaged, so you don't need to go through the hassle of setting this up. So in less than a couple of minutes, you should be able to get machines spin up. And we have CloudFormation templates available as well to set up your training cluster. But let's say you're getting started, right? Like, I want to get my toes dipped. Like, hey, I don't have a car. I don't have data. Like, hey, I want to get it. So where's the data, right? We actually need to start fiddling with some of this technology. So I curated a list that might be useful for people considering getting into this field and seeing what are the capabilities. To divide it into two different sections. One is the object detection and the self-driving aspect. So object detection, obviously we want to detect people, things that are normally we see in a driving environment, right? Like buildings, trees, people, I don't know, maybe deer, which we want to avoid. So on the self-driving side, we do have data sets from like Oxford, MIT, where they've actually done labs and so on, where you can use and see if you can develop those algorithms, whatever algorithms, or maybe whatever you've developed, how does that work? So this will be quite useful for you to go start dipping your toes into this field. Now, again, like, let's say you now have a platform, you're trying to build a solution, right? Like, it's more important that we always start with data, right? Everything starts with data. So here are a few mechanisms to get data onto AWS, right? You could do a direct upload on S3, direct connect, and so on, Kinesis. These sort of work well for most use cases, but with the kind of scale that we talk about, it just might not be, when you're thinking about sending 20 terabytes, you can do the math on, like, say, 100 Mbps line that might take about a week or more to actually get that ingested, right? So we need a different mechanism. And this is where Snowball comes in, where you can ship that data securely to AWS. So it's going to be far cheaper to get that in. If that doesn't fit, we have Snow Mobile, IoT services. And of course, if this is a generic slide with all the ingestion that we have. And of course, like, you store it in S3, which becomes your data lake, and where we can spawn up different services, or actually process with EMR and Spark to get it meaningful for the ML part. And then the next aspect is, we talked about EMR. You can actually use, say, Redshift or Athena if it's already in kind of a structured format. And if not, then Glue is a great tool to do ETL, process it into a state where you can actually start using the data in a meaningful way. Not to leave out mTurk, right? As we said, like, it's not just collecting a lot of images is enough. We actually need them labeled, because more often than not, for parts, we end up doing supervised learning, which is data with a label. So we actually know, hey, in this image there are people, in this image there are buildings, or there are cows, and so on. And there needs to be labels. So mTurk is where you can get human workers to annotate your images. So pretty important in this flow. So, okay, we talked about this, right? Like, when we're talking 20 terabytes of data, like, it's hard to ingest. And this is where Snowball Edge comes into picture, where we can actually not just ship the device with a 100 terabyte drive, so maybe 5 days worth of data, but it actually has onboard compute. So while it's traveling, if you did want to kind of pre-process the image as it gets into the cloud, that is very possible with Snowball Edge. If that doesn't fit, well, you can always get a snowmobile and get 1 petabyte of data shipped in to one of our data centers. So this is another option. OK, so I think we've talked a fair bit about the environment, so I thought it'd be fun to actually code and build a couple of networks to see what this is all about. So this is, I think the first network I'm going to show is behavioral cloning. So this is where it's the most simplistic way to get a car to learn to drive by itself. So it's imitation learning, which is anybody with a car drives it around, and what you do is it learns to drive almost like you, maybe a little worse than what you drive. So it's imperative that you drive well when you collect the data. This is actually on GitHub. I'll share the link a little later. So what we do is we've actually captured the image. The data set looks like we have an image, and in the image, we actually have steering angle and throttle, that is the accelerator, recorded. So we record that. And the idea is that given an image, we're going to predict what is the steering angle so that the car stays in the lane or between the lines so that we can go around the track. That's the objective here. So this data set has been uploaded, and there's a blog as well on this. So what I've done is I built a function that's returning me iterators there. So we usually split our data into a training set and a validation set, classic technique. The idea is we don't want to overfit, right? So we're trying to build an algorithm. We want to not show it all the data, because ultimately, the network or the final deployment of a machine learning model is never going to be exactly the same data, right? So we hold back, and so that allows us to see if it's generalizing as we train. Now, what we can see is the model itself fits in, less than a screen. So it's fairly simple. What we do here is we use a convolutional neural network. The idea here is the images. Anything dealing with images, we rely on localized features or local spatial information. So we aggregate all these local information and see how they interact with each other. And based on that, we actually understand a global picture of what's happening. So we have a two-layer convolutional network here. And usually with the neural network, we'll add an activation function. The idea is we are adding nonlinearity, because these problems are not simple enough to solve with linear models. And then we add what we call as two fully connected layers, so that all the convolutional features that we have learned, we need to tie that into how they interact with each other. And then we run it through the linear regression model. So in this case, in simple, I'm only going to compute the steering angle, not the throttle. So the linear regression is going to give us a single output, which is going to be the steering angle. So let me actually run code. And this is what our network looks like. So we can visualize our network here, where we go with a 120 by 160 image. We're using only a single channel. That is, we're using a grayscale image, not RGB. And as we go through, we do a bunch of matrix operations, and it goes up, and then finally the fully connected layer here. So we specify a batch size. We never usually train with just a single image. The idea here is we're using GPUs for compute. We need to train in parallel, because otherwise we're not utilizing the hardware completely. And there's also no reason to, training is faster that way. And we're using just one GPU because the data set is not that big here. And so once I've defined the module, I can just give it the training data set, the test data set, and then finally the loss metric, which is going to be MAE, stands for mean absolute error. The idea is we need the loss function to tell us, like, hey, I've predicted something, how far am I? And given this is the Euclidean space, it's the MAE difference, if we kind of plot how it goes, it's a much smoother transition than, say, if it was quadratic, which would be like a parabola. So I'll just kick off the training. And we can see that the error on the left here keeps decreasing, right? So it's going from 17.174 all the way down to 0.13. That means we're making progress. The network is starting to learn. And so the good thing with some of the visual algorithms is we as humans can interpret them for most use cases. So it's easier for us to say, hey, how good is this algorithm doing? So, oops, it's not required. Sorry, I need to. So we've only trained it for 10 epochs. Let me load the model. And the idea is, let's actually just spot check, what our network, whatever our network has learned, right? It's not quite a perfect network, but we can actually see, hey, I was supposed to, predict 0.1. That's kind of how I drove, and my prediction was about 0.3, right? It was a little off. So this is just spot checks that you can do when you train a model. But the fun part is, what I thought is, hey, why not actually try and build a simulator where you can drive like a fake car and see on the prediction. We sort of know how we need to stay between the lines. So let's actually see if the car does that. So here's some code on, we basically we have a rectangle. And what I'm doing is I'm doing the prediction here on an image. I get the output angle, and here's the simulator. So it's actually staying between the lines. It's turning left. It turns left. It does know to turn left. It sort of stays between the lines. So now we know that this model is fairly workable, right? So once we have done that, it's time to deploy it in the real world. So more images, right? Like the training data, these deep learning algorithms are data hungry. So what you want to do is be able to augment the data, collect more data, a lot of simulations to enhance the data so that we can actually get much better models. Because it's very expensive when you think about the deployment aspect, right? Like if you have to, oh, well, I've got a new model, let's run the car, oh, it crashed. let's go back. So you need more guarantees when you deploy so that it's more efficient in terms of resource utilization. So that's the driving aspect. So next code I want to show is actual object recognition. Object detection is a little much more difficult. I thought it wouldn't fit in the time here. So it's to build actually a classifier. So I'm using Gluon, which is a higher level interface, or MXNet, which is developed in conjunction with Microsoft. It's easier interface for developers to get started with deep learning. It's simple, right? Like anybody who's given a driver's license test, usually you have to identify some of these signs. And now we're trying to get like an algorithm to see if, hey, that's a stop sign versus that's an arrow bridge, and that's a yield sign, and so on. So how do we build that classifier? So this is actually called the German traffic sign dataset. It's available free. Just for ease, what I've done is I've actually pre-processed the images into a Python pickle file where I have features. And also these images, we don't necessarily need an entire image, right? Like we don't need a 4-megapixel image to say it's a stop sign, right? You can kind of sway, even if it's a little small, we can do that. So we actually subsample the images because it's faster to train that way. So the images we have is 32 by 32. And usually it might be a good practice to do that because based on your problem, you might not require the entire image, or the image resolution, rather. Sorry, let's do the shape. So as you can see here, we have about 40,000 samples, 32 by 32, and 3 channels. In this case, we'll actually end up using the RGB channels. So in our data set, what are the signs, right? Like, hey, we have speed limit signs, stop, no vehicles, slippery road. This is a classic data set. And we've got 43 of those. And usually, depending upon which framework you use, usually the data format shape is is like you'll give the batch size, the number of channels that you have in an image, in this case 3, and 32 by 32. In the last example, we had batch size 120 by 160. So what we'll do is we'll just normalize the data here. So we've got the training set. We're just going to divide everything by 255, just normalize that. Next thing is we'll actually load it into like a training iterator. In this case, it's called data loader. So we'll load that data. It's pretty fast. So to actually help build these convolutional network models, what I went ahead and did is built like a nice class which actually helps us build convolution networks in like 4 lines of code. So to build a convolution network, like all I need to do is specify these 5 lines of code, and we're good to go. But unlike other frameworks which are symbolic, which are sort of 2-level, where you're writing the framework language, it compiles down, and then it executes. Think of just like SQL, right, which is declarative. Now it's hard to debug that because where do I put a breakpoint if I need that? We have to rely on a lot of print statements. So because this is completely imperative, you can put a breakpoint anywhere and debug through the code. So I can execute this code. So what we're doing is we are using a 2-layer convolution network with 20 and 50 filters. It's going to train. I think it's going to take a better time. OK, there you go. So not bad. Like one epoch, we were saying, hey, on our test set, the accuracy has been 85%. So the idea, I would say, is like always look at the test set accuracy. That gives you a good idea of how generalized the model is. And I see it increasing. So all a good sign. Actually, I don't have. Let's give it a couple more seconds to finish the epoch so that I can show you how well we've trained and give an example and see if it can actually detect a sign. So you can see like our training accuracy on our data set is already at like almost 100%, but the validation accuracy is still at 92. So this is what we did. Our validation accuracy is sort of following and flattening, and our loss function has decreased. So what you want to see is a nice decay, like exponential decay. So next thing is, let's actually check out, so this is the, oops. So let's actually check the image, right? Like, so this is the image we want to classify, and let's see if what we trained can actually detect it. That was pretty fast. It says that's a stop sign. So we've successfully classified image that was not in the data set. Right? So these are a couple of examples on how easy it is to get started. There's a lot of code out there, tutorials. So I encourage you to go explore some of the data sets, get started on deep learning, especially with these autonomous driving use cases, and get yourself going in this area. Okay, so just to recap, right? To set up the environment, go to the deep learning, go to the EC2 console, pick up the deep learning AMI. It's available at no additional cost, and you can spin up on most of the instances. But if you want to do faster training, use the GPU instances. You can set up a SSH tunnel to use the Jupyter Notebook. So the data set I showed you was from actually a robocall rally that we're doing here at AWS. I'll talk about it a little more later. The data set is available there, and you can just clone that GitHub repo and get started to build your own algorithm, better than probably what I have there. Again, how can you build a convolutional network in MXNet? It's, again, fits in one slide, right? You declare your convolution layers, then you're going to have your fully connected layers, and finally, whatever the output that you wish to have. This is a classification network, so we'll use a softmax output. What about, we talked about algorithm development, right? Like we have a whole slew of other services, and people want to interact. Like, how do you interact with other vehicles? How do I connect to the cloud? How do I securely communicate? Like all these aspects. So we actually wanted to put together a reference architecture so that you can replicate this, extend this to actually have local connectivity, sophisticated event rules, data processing and storage, both locally and in the cloud, right? So we have, with Greengrass, what we get is a local broker that manages these Lambda functions. We can have local user Lambda functions that are doing tasks, whether it's extracting things from sensors or sensor fusion, and so on. Again, as I mentioned, security. So we actually are talking over HTTPS, a secure connection. In this case, X509 certificates, we can get them down to the actual edge device and run that. Device shadow, you might want to actually have a state of the car in the cloud and kind of like sync between the cloud and the car. So that's possible as well. So what are the components here that get? So we start with the data ingestion, right? This is, if you remember the slide earlier on kind of parts, this kind of brings this back all together on each of these components. So we have the connected data vehicle ingestion, right? So we have, through AWS IoT, you can ingest data into AWS. What you can do there is set rules. Via the rules engine, depending upon a certain sensor, you can direct it to, say, a different DynamoDB table, or you want to actually ingest this data into Firehose and finally into S3. You can do that as well. So that's one aspect of the data vehicle ingestion. The other aspect could be just analytics, where you want to show people a dashboard of what's happening, how fast you've been, and so on. you can use hook it via another Lambda function onto DynamoDB or by API gateway and get that data onto the dashboard. And then we have, you can actually have, once you have ingested the data, right? So you can, let's say you're ingesting the data into Kinesis, you can do anomaly detection to identify, say, faulty sensors or patterns that, hey, this driver is not driving, sort of safe, so let's actually send a feedback, and at the dashboard, alert the driver that something's happening. So all of that can be done. And remember, you're always going to have more compute in the cloud than local. So having a hybrid architecture or saying who's responsible for what, or having the cloud kind of correct local decisions because of availability of power or compute power in the cloud, so you can have this collaborative architecture. And of course, at the back end where you're doing analysis of these vehicle data, you can use our visualization tools like QuickSight. You can use some of our partner solutions as well once you get your data into Redshift and so on. So customer stories, right? Like who is actually developing these algorithms today on AWS, and what are people working on? So one story is too simple. So they're using MXNet to actually build really sophisticated algorithms. In this case, they're doing a MASCAR CNN-like approach, where they're segmenting each vehicles and being able to identify them with pretty good precision and recreate that in almost near real time. What they've been also successfully they actually did a autonomous truck drive in Arizona a couple of months ago. They did about 100 miles, I believe. Also, they use simulations. You can't. It's really hard to collect data and good data. So sometimes it's easier to do a simulation of certain kind of data, which might be really hard to occur in practice, but you want to make sure you've covered all these edge cases. So another example is Mapillary. It's a cool company. They actually use crowdsourced data, and stitch the data to create maps. So they've been able to combine 142 million user-submitted images and map about 2 million roads. In this case, they've used Caffe and TensorFlow on top of AWS P2 instances to be able to do this. Another cool example is drone navigation by Iris Automation. So they've actually done deep learning to help the UAV drones to detect objects and avoid collisions. They've actually used the P2 instances again, and also deploy on the edge on the vehicle, which have the TX1 hardware, where they're actually ingesting video and analyzing the frames and doing the predictions and collision detection. Couple of things. So we actually have an autonomous driving hackathon, which is happening today. And here are a couple of clips from today where people are trying to build the models. So here's one of the cars that has been able to drive by itself on doing a lap. So these are little cars that are running Raspberry Pi, where we actually train them on AWS. So we collect the data. So what you saw there with the behavioral cloning example that I showed, this is exactly the model that we're using to train there. So we've done a few laps. It's actually collected those images, and we use that. So we're trying to do a little bit of object detection now and see if it can actually detect and do the needful. So let's see what it does here. So it didn't. So it did come back on the track there. So, but on a good note, it did see the sign and it was able to avoid the car, avoid the person, and the stop sign. So if you're interested, like I highly recommend to come actually with us at the Robocar Rally. So we're going to have a race at 9 p.m. today. We've got limited seating, so come by to the Aria Ballroom 6, Pinion Ballroom 6. It's going to be a fun event. Yeah, thank you. Thank you so much, guys.